Hello, today we're going to look at Heisenberg's uncertainty principle, which generally relates to things at the atomic and subatomic level. Heisenberg's uncertainty principle is usually written in this form: delta x times delta p is greater or equal to h bar over 2. What does that mean? Well, delta x talks about the uncertainty in position. If you want to know, for example, where an electron is, how clear can you be? How precise can you be about where it is? Delta P talks about the uncertainty of that electron's momentum. In other words, its velocity and its direction. And the idea is that the uncertainty in position multiplied by uncertainty of momentum is greater than h bar over 2. So you cannot precisely define position and momentum at the same time. Here is, let's say, an electron. That electron has a certain position, x, and it has a certain momentum, p. But we cannot measure both of them at the same time. The reason for this is that electrons, even atoms, are very small compared with anything that you're going to use to measure them. For example, let's say we used light to look at an electron. Well, here's a light wave which goes right past the electron without even noticing it. In fact, I haven't drawn this to scale at all because a light wave has a wavelength of approximately 5 times 10 to the minus 7 meters. Whereas even if this were an atom, it would be approximately 10 to the minus 10 meters. If it were a proton, it would be 10 to the minus 15 meters. And if it were an electron, it would be something like 10 to the minus 18 meters. In other words, even an atom is 1,000 times smaller than the wavelength of this light. A proton would be about 100 million times smaller than the wavelength of this light. So any visible light will just go straight past the electron or the proton or the atom without noticing it. If you want to actually see something of the size of an atom or a proton or an electron, you have to use some form of radiation whose wavelength is broadly comparable to the size of the thing you're trying to see. And therein lies the problem, because the smaller the wavelength, the larger the momentum. It's given by a formula that says that the momentum of a wave equals h, Planck's constant, divided by lambda. And so you can see that as lambda gets smaller, p gets larger. Where does this formula come from? Well, we can derive it in a simplistic way. We take the famous formula of Einstein, E equals mc squared, and we say that momentum is classically given by mass times velocity. Now, when we're talking about electromagnetic radiation like light, photons, which are the constituent parts of that light, don't have a mass. But we can say that the mass of a photon is kind of equivalent to E over c squared from this formula here. Mass is E over c squared. And so you can say that the momentum is the mass, E over c squared, times the velocity, which is c, and that gives you E over c. But you'll know that energy of an electromagnetic wave is hf, Planck's constant, times the frequency of the radiation. And that is known as the packet of energy, the photon packet of energy, the quantized energy. And so now we can say that P, the momentum, is E, which is hf, divided by c, but c over f is lambda. And so we derive the formula that we started with, P equals h over lambda. And now we can see the problem, that if we have an electron, or a proton, or whatever, and we send in very low wavelength electromagnetic radiation in order to be able to see this proton, it's going to have such a high momentum that although the wave may well reflect and we can detect it, it will give a huge kick kick to this electron or proton and send it scurrying away. It's rather like hitting a billiard ball with a super fast billiard ball that knocks it for 6. And so you can't tell what its position and its momentum are. We can perhaps explain this by reference to the so-called single slit experiment. This is where you take a single slit, very narrow, and you pass ordinary light through it. And what happens is that the light beam comes through the slit, but as it goes through the slit, it spreads out onto a screen. And what you find is that the intensity of the light on the screen goes something like that. In other words, at these points it's virtually 0, up here it's very high, and it doesn't get very much bigger thereafter. So it's a kind of a spread out across the screen, and the spread is at an angle theta. Why does it do that? Well, if we magnify the slit, we can see what's actually happening here. Here is the slit of dimension d, and here is the wave that is going up to reach this point here. In other words, the point where there's no light at all. Now, if we drop a perpendicular here, this angle, as we've said, is theta. That's that angle there. And by geometry, this angle here is also theta. Now, what will cause these two waves, when viewed by my eye here, to cancel out? By cancel out, I mean that one wave will look like this, and the other wave will look like this, and when they are superimposed, they will simply produce a flat line, which is the no light that you get here. Well, the answer is that they have to be completely out of phase. And how can that happen? Well, that happens if this distance here, from here to here, is lambda, because that's the difference between the phase of this wave and this wave. Why is that the case? Well, let's blow this up again. Here is that famous triangle. This is D, this is this gap here. This is lambda, that's there. And take a point halfway. Now, this is lambda over 2. And this wave and this wave are going to be half a wavelength apart. And so they are going to be in precisely this position of superimposing. So the light there will cancel the light there. And the light there will cancel the light there, because they're all lambda over 2 apart. And similarly, every position here will cancel a position here. Every point here, every point there will cancel there. Every point there will cancel there. So all the points in the upper half cancel all the points in the lower half and produce this minimum here. And you can see that from this diagram here that lambda equals d sine theta. So if you know the wavelength of the light, you know what the angle is where you're going to get a minimum. You can do the same thing, instead of using light, you can do the same thing with electrons.